In the past, you've most likely learned about increasing and decreasing intervals of a function. We did talk a little bit about maxima and minima previously. So I'd like to introduce a few other things and then talk about how those things are affected by derivatives. So here's a graph. It's a pretty simple graph, and I just want to point out a few features on this graph. So the first thing is the stuff that you kind of already know. This point right here is what we call a local maximum. And actually, in addition to being a local maximum, it's also the absolute maximum, meaning the highest point of the graph. This point right here is the local minimum. And the endpoint that we have on the left is my absolute minimum. By the way, the endpoint on the right doesn't really have any sort of special designation. So that's the stuff that we did previously. So now a few new things. So on this graph, from this first point to this point right here, we say that our function is increasing, meaning that it's growing, the y value is getting bigger from left to right. It's also increasing right here. So we have several intervals of increasing. So the other thing is that right here, you might be able to guess, our function is decreasing. I'm hoping that you saw this last year and that you kind of remember it. There's one other thing, and I'm not sure if you've seen it or not, but so it might be new, and that is what we call concavity. So concavity, we say that something is concave up if the curve of the graph is kind of facing up. You can think about what a parabola looks like. This thing right here is concave up everywhere. On this graph, you can kind of look at it and you'll notice that at this point right here, it kind of changes so that I have this thing that looks like a parabola. It's actually concave up at that blue point right there, at that blue area. And the opposite of concave up is concave down. So concave down is going to look like an upside down parabola. Looks just kind of like that. And you'll notice that this graph has a downward concavity right here. So the last thing that we have that I think is probably most likely new is the point where our graph changes concavity. That is called the point of inflection, or inflection point. So our inflection point is, or point of inflection is the place at which the graph changes concavity. So let's talk about how to find this stuff using calculus. So our first little rule has to do with increasing and decreasing. And if our graph is increasing, that's at that point our derivative is going to be positive. And when our derivative is negative, that means that our function is decreasing on that point. Our second important thing has to do with local extrema. So if my derivative changes from positive to negative, meaning the function goes from increasing to decreasing, then I have a local maximum at that point. And if it goes from decreasing to increasing, meaning it goes from negative to positive, I have a local minimum. I think that these definitions are a little bit hard to follow without a picture, so I'll go ahead and draw you something here. So I have a function f right here, and I want you to notice that up until that yellow point, my function is increasing, which means that my derivative is positive. The other place where my derivative is positive is going to be at this place right here. My graph is increasing there, so my derivative is positive. However, when my graph is going along, once it reaches that yellow point, the derivative then is going to become negative. So my f prime there is negative. So what that means is that at that yellow point, that is my local max. And when my derivative changes from negative to positive, that's going to happen at that red point. That's going to be my local min. So if you have trouble understanding these definitions, I think drawing a picture usually is the easiest thing to do. Just remember that you're increasing when your derivative is positive and you're decreasing when your derivative is negative. So in this example, we're going to find the local extrema, meaning the local min, local max, and then we're also going to find the intervals of increasing and decreasing. So the first thing you always want to do on these ones is you need to find your critical values. And we're going to do that by finding our derivative and then setting our derivative equal to 0. So our derivative of f of x is going to be 3x squared plus 6x. When we set that equal to 0, we can factor out a 3x. We get x plus 2 is 3x times x plus 2 equals 0. So I have critical values at x equals 0 and x equals negative 2. Now you'll notice I didn't actually, I still haven't figured out where my extrema are. I can, if I want to, find, and I will actually want to do this in just a minute, I can find my y values. I will need that when I find my maximum and minimum value, but that's not going to tell me everything I need. You sometimes will get a critical value that does not actually have a local min or a local max, so be really, really, really careful. The way that we can test if something is a local minimum or a local maximum is actually the same way that we're going to find intervals of increasing and decreasing. We're going to make what's called a sign chart. So when we make a sign chart, we need to look at all of the intervals on our graph between our critical points. So when I make my sign chart, it's actually going to be a chart and the numbers are going to be in order. You can kind of think of it like a number line if you want, where I have negative 2 on my number line and I have 0 on my number line. But I'm actually going to extend it out. So I'm going to have 3 important intervals. I'm going to have where x is less than negative 2. I'm going to have where x is between negative 2 and 0, and I'm going to have where x is greater than 0. That's going to cover all of my intervals where I could potentially change signs of my derivative. The next thing that we're going to do is figure out if the derivative is positive or negative. We do that by choosing a test point. And the test point can be anything that's actually in the interval that's not on the one of the actual critical values. Just note that if you were to choose like x equals 0 or something, you would get that the derivative was 0, which is good because that's what we actually want to choose our points for, but it's not going to be very useful for this. So my test point I'm going to use when x is less than negative 2, I'm just going to use x equals negative 3. And then I'm going to substitute that into my derivative. So I get 3 times negative 3 times negative 3 plus 2. You'll notice that I took the factored form there. It makes it a little bit easier. The other thing that's really useful for this is you don't actually have to do all the work for these problems. Like if you have a fraction in there and you know if each factor, like this one I know right away looking at it that it's going to be a negative. If you know each factor is negative or positive, you can just you can just use that. I'll show you an example of that later on. So what we're going to find is if we multiply everything here out, we will get a positive value. That's a good start. That means our graph is increasing when we're less than -2. I'm going to do the same thing for this middle interval, and -1 is the most logical point to choose. If you want to make your life difficult, you can choose like -1/2 or -3/4, but I don't really recommend it. So same thing, I'm going to find my my derivative at -1. I need to determine if it is positive or negative. Sorry, I'm running out of room here. I will find that my derivative at that point is negative. The last one, choose any point that's greater than 0. I'm going to find f prime of, I'm going to use 1. So once I substitute 1 in, I will find that my derivative is positive at that point. So that means that it's going to be increasing there. So I can put my increasing and decreasing intervals in right away. You can use interval notation if you prefer. Actually, they don't really care what notation you use on the AP exam, so interval notation is fine, but you don't necessarily need to. You're welcome to also just use the inequality notation that I use right here. For the local max and the local min, do remember that I need to do a little bit of work to find it. My maximum and minimum values are the y values, not the x values. So let's take a look at the two critical values. There's a good chance that one of those will be a max and one of those will be a min. What I would recommend doing is kind of just try to draw a quick sketch. So I know that this is -2, this is -1. So I know that my graph is increasing until I get to -2. Then it starts decreasing, and it decreases until I get to 0. Once I get to 0, then it increases again. So it kind of looks like this. So if you draw something like that, you can, that's a quick sketch. It is not the actual graph. But you might be able to see then that I have a max at -2 and I have a min at 0. So I think that that's usually pretty helpful. So I'm going to write out some work. So my maximum I can find by finding f of -2. Remember, you need to plug in your -2 to the original equation, not the derivative. If you plug it in the derivative, you'll get 0. I have a minimum at f of 0. The other thing I'm going to tell you to do, if you draw a sketch like this is not the actual sketch of the graph. If you're on the AP exam and you draw a sketch like this, everything that you write down has the potential to be graded unless you cross it out. So I'm going to cross that out after I used it. Okay, so the last thing I'm going to do now is to find my max and min. I am going to substitute in -2 back to in my original function, and I do the same with 0. With -2, I end up getting 6, and with 0, I end up getting 2. So don't forget that your maximum and minimum are the y values, not the x values. We do have one more thing I'd like to talk about, and that is concavity. So I mentioned concavity a little bit earlier on, and my graph is going to be concave up at intervals where its second derivative is positive. By the way, this I means in an interval. My graph is going to be concave down when the second derivative is negative. So we have what's called an inflection point. I did mention that. If your graph changes concavity there, and also your graph has to be continuous there, but the key thing is that it must change concavity. In other words, your f double prime must change signs. So you might occasionally have a place where your second derivative is equal to 0, but it doesn't change signs. that's not going to be an inflection point. It's only going to happen where it changes signs. So to find inflection points and concavity, you actually follow the exact same process that we did previously with increasing, decreasing, and local min and local max, except that you do it with a second derivative. So we'll do a few examples like that in class.